Yeah, okay. Let's next talk is let's welcome Matthew from the University of Melbourne, and he gave a talk about random dimensional curves over S1 associated with two matrix model of the sorry, Chiral Hamiltonians. Sorry for the
Yeah,
pronunciations.
Carol.
Thank you,
Yeah,
Matthew.
well, thank you for the introduction. Hello, everybody. It's pretty good to get the opportunity to give another talk to a matrix related event. It's always a good time. The presentation I'm going to give today is modified version. Actually, I also been invited to Matrix in Creswick about a month or two ago, and I also had the opportunity to give a talk there, and very much appreciated. So for today, I would like to have sort of informal, rigorous enough walk through a fairly recent topic on integrable system and random matrices. In that case, over the circle. So in a moment, I'm going to say a bit more precisely what I'm talking about. Uh, yeah, so all right, let's get started without further ado. First of all, I would like to give you a brief overview about the connection between topology and random matrices. I think it's a good first step in the door. All right, so we'll start with a fairly simple model, which I denote A here. All right, so this is an application. This is a map from R plus times 0 to pi to the set of 2 by 2 symmetric real matrices, right? And if you fix the radius r, you can see it as an application over the unit circle, right? I'm simply identifying 0 to pi with the unit circle. Okay, and fairly straightforward computation shows you that regardless of the value of the angle which you're sitting at on the unit circle, you would have essentially two eigenvalues, eventually with a degeneracy, right, which are 1 plus and minus r. Okay, I put a little picture to show you visually how it shows on the 3D space in Cartesian coordinates, right? This is actually a fairly well-known matrix model for physicists as it models naturally the quantum spin in a magnetic field, right? Um, but perhaps more interestingly, um, it's fairly natural to investigate eigenvalues, but here nothing that surprising happens. However, if you move at the level of eigenvectors, then something quite remarkable happens, and you can already see here I wrote explicitly to normalize a choice of two normalized eigenvectors, right, depending on theta. And I don't know if it strikes you immediately, but the matrix model here that we chose was 2 pi periodic over the unit circle, right? As pi winds from 0 to 2 pi, it comes back where you started. And same goes for the eigenvalue, but quite surprisingly, the eigenvectors are not 2 pi periodic. There's some sort of obstruction there, right? And so, yep, let me go one step further. You see, that non-2 pi periodicity is the first step towards something a bit deeper, non-trivial about these eigenvector for random matrices. And later on, I'll also maybe say a word about eigenvalue because they can exhibit the same kind of obstruction, right? So my way to understand, I mean, it's maybe not the most standard one, but my way to understand this kind of obstruction is to ask naive questions, stupid question one might say. So in that precise case, for that specific choice of matrix model over the unit circle, we see that we get a non-2 pi periodicity. However, we get something which is 4 pi periodic. So one might ask, well, how about something 6 or 8 or 20 pi periodic? Can we get essentially any period, and can we get a periodic collection of eigenvectors over the unit circle? And you might also ask or wonder what happens if, for example, the matrix was complex valued, right? Well, it turns out that if you change your point of view, and you can bring a fairly satisfying answer to that question, it turns out that the collection of all eigenvectors for this matrix model over the unit circle forms what people refer to sometimes as an I section of a vector bundle, which in that case is equivalent to the Mobius strip, right? And this is really a good way to pinpoint the sort of obstruction that happens at the level of eigenvectors, right? Because if you want the collection of eigenvectors it forms some sort of section of a line bundle over your base manifold, which in that case is S1. And or I'm not too sure how people are familiar with that, but essentially over the unit circle, you get two kinds of line bundles. So you get the trivial one and you get the Mobius strip, which essentially tells you that, it brings an answer to the first question I put before showing that slide. So you're either 2 pi periodic or you're not, and you either get a +1 as a coefficient or a -1, and that's the two possibility you can get, right? It's nothing else happening. And you also see that, for example, it cannot be aperiodic. It actually has to be 2πn periodic, right? It has to be a multiple of 2 pi. And in the complex case, actually, is also a bit deeper reason why it can be aperiodic in that case. It's much wilder in some sense. Okay, so let me just check. Okay, I'm on time, cool. So that was just a little short introduction to motivate. Oh, sorry, cat is. Sorry for that. Just a little motivation as per why there is deeper connection behind these random matrix simple stuff. So for today, I'm gonna up the dimension a little bit, and I'm gonna make the matrices random, right? I'm gonna bring some randomness into the matrix model, but I'm still gonna look at models over the unit circle. It's a very good to model to build theories and ideas. Okay. I'm also going to say a word about the physics motivation of the present work. It is rooted in physics, actually, and it's something that has been investigated first by physicists a couple of years ago, right? So that whole story stems from the study of disordered crystal, essentially, right? So in the one-dimensional case here, but later on, I hope for higher dimensional, like 2 and 3D would be very interesting. Anyway. And we're interested in system with edges, as it turns out, it's pretty important, right? So looking at some sort of disordered crystal, one-dimensional, typical model of that would be a polyacetylene molecule with n sides. Okay, and it turns out that in that setting, the Hamiltonian that models one particle in that system has a pretty specific form, right? Which you can read here. So the Hamiltonian would be H. T is the crystal momentum around S1. And so we have that particular block structure, right? It is chiral. For those of you who are familiar with the Atlansian-Bauer classification, we're working in the A3 class, essentially, one dimension. And okay, for the sake of simplicity today, I'm going to skip a bit of the story, but we classify those Hamiltonian through the winding number of their upper left block. And I can see there's a typo in my slide, so apologize for that. So it should be the winding number of P maps to that of KP, not H of P. Sorry for that. Right. So as I said, the system is assumed to be disordered. So for example, you get some impurities along the crystal or that kind of thing. And so we're going to study, to start with, the winding number of the determinant curve, right? That takes a point on the circle and maps it to the determinant of KP, right? Again, I'm going to skip the basic complex analysis, tools. I believe it is a fairly standard object, right? And perhaps more interestingly, we study such a random winding number with a partition function, which you can read on the right part of the slide here, which is what I call Z index M, and the N reflects the size of the random matrix, right? So here P and Q were 2 points, two collection of points on the unit circle, right? And so I draw 2M points on my unit circle, and I form that that partition function. And after that, by taking successive partial derivatives and by colliding the arguments per se, I will be able to recover the k-point correlation function for that random winding number, right? So in the present work for today, I'll probably talk about something to be published and be put in the archive probably in the next few days or weeks. So I'm going to talk about the first moment of the winding number. Okay, so probably enough for today. Okay, so you can see on the left part of the slide, how do we study that average winding number? Essentially, we just take the partition function for one terms in the product, and then we take a partial derivative and we put the same the two arguments to be equal to each other. Okay. So as I said, that thing stems from a physics question, and the whole thing has been investigated first in 2021, right, for a fairly simple model, which is that KP here is so a two matrix model. It's a sum of two random matrix, G1 and G2, with deterministic coefficients, right, who are function over the unit circle here, cos and sine. So I think there's a slight imprecision here. In their original paper, what they mean by P should be understood as a theta over 0 to pi, right? Whereas I count it as a point which should be represented as exponential e theta. So there's a slight imprecision here. P should be understood as a theta here, right? Original paper is a little confused in that sense. And so it turns out that the first correlation function in that paper was 0. And there's a good reason why. And at the level of the second correlation function, they also had some interesting function, which has a nice scaling limit. I might say a word about that. I'm not too sure. No, well, keep it short for today. So maybe in the future. Okay, and two years down the path, there's been an extension of that simple model, where this time the cos and sine function have been replaced by arbitrary smooth complex value function on the unit circle, which are denoted by A and B here. And using some invariance arguments, some SU2 invariance argument, actually, they've been able to derive pretty elegant and pretty simple form for the partition function as associated with that random winding number, right? So that model actually has a fair lot of integrability. This is a bit this is really nice. It's music to my ears, really. And what's more, it's also been so in that case, the two random matrices G1 and G2 are n by n with complex entries. And what's more, the entries are random and run from a standard normal distribution. Okay, but that partition function has also been computed in a real setting. However, the coefficients are basically a nightmare in that case. So I'll just put them under the rug. Just know it's up there somewhere. It involves Pfaffians and Pfaffian process. It's really a nightmare. So for today, just enough to know it exists somewhere, I guess. Yeah, so as I said, for today, I would like to show you a result, and in particular, interesting asymptotic expansion of the average winding number, that determinantal curve, right, beyond the Gaussian case. So for a larger class of random matrices, it's fairly robust results. I'm going to stick with two matrix model because, as far as I can tell, and as far as other people engaged in that area of study are concerned, this is as far as we can go to get integrable structures and to get exact formulas. If you go beyond the two matrix model, we lose integrability, and we can't say much, or we have to stick with loose estimates, but we lose a lot of integrability there, right? So I'm just going to show you a few pictures to have a mental representation of what we're talking about. That's the kind of determinantal curves in the complex plane, right? So it's the determinant of that two matrix model as the base parameter 1 around the unit circle. So of course you get a closed loop in the complex plane. um, well, they pleasant to the eye, but so those matrices correspond to the first model initially investigated in 2021. They're pleasant to watch, at least for me, but they're a bit misleading because they contain a lot of symmetry that's reflected by the inherent symmetries of the base function cosine and sine, right? It turns out that if we generalize it a little bit and if we drop that symmetry, the resulting determinantal curves are not so symmetric anymore, although they wind a lot. So um, there's reasons why that first model was misleading in many ways, and there's some features that you can see with such a choice of symmetric function. I'll say a word about that a bit later. Cool. I think that's enough for the physics motivation. All right, so next up, I would like to give a brief overview of the central random matrix tools I'm going to use. Some of you might be familiar with some of them, but a good reminder on the way doesn't hurt, I reckon. So for today, I'm going to deal with a class of n by n random matrices, so matrices of size n with complex entries. And what's more, I'm going to require that the eigenspectrum has some sort of isotropy. What I mean by that is that the probability distribution is isotropic, preferred direction, right? And so I'm going to introduce a class of random matrices that generalize the well-known Gini unitary ensemble with complex Gaussian entries, which is not that well-known, actually. I mean, I had the privilege to give a few talks about it, and most time people never heard about it. So it might be something you can take for today and put in your pocket. These random matrices are parameterized by a single function, which is called a Polya weight, right? And what's more, we require that both the collection of singular values and eigenvalues form determinantal point process, which, as some of you might know, it's a structure that also holds a lot of integrability and opens the gates for a lot of exact computation, right? So we want the collection of eigenvalues and singular values, which are the eigenvalues of the hermitization of the matrix, to form determinantal point processes. And what's more, we require that those classes of random matrices are closed by product and inverse, right? Which is a very strong property. It brings a lot of rigidity and it restricts a lot kind of random matrices we can deal with. All right. So yeah, here you just a bit of technicalities. As you see, we define some sort of generalized inverse and some it's a convolution product actually of associated weights of this random matrix ensembles, because we're studying two matrix model, and to study the partition function associated with two matrix model, we use an algebraic trick to reduce the two matrix model to one matrix model using that closure by inversion and products. I think you put a word about it on the next few slides. Right. So before jumping there, I'm just gonna give you a very brief example, which some of you probably heard about before, which is the Gini unitary ensemble. Right. It's the first model to have been investigated for those random weighting numbers. We just require all the entries to be independent and normally distributed according to a standard complex Gaussian random variable. Right. And from that, it's fairly easy to derive the matrix probability density on the set of n by n the matrices. And in the previous formalism that I've mentioned, the weight, the Polya weight, is simply the exponential function, exponential minus t, right? And it is also fairly straightforward using, for example, the Shor decomposition to obtain the joint density of eigenvalue in the complex plane. So here on the right, you can see a realization of probably 500 or something eigenvalues in the complex plane. Okay, so that's kind of, can give you a mental picture of the kind of random matrix we're dealing with. And here is a perhaps a bit less classical example, which is the complex spherical ensemble. So in that case, we just simply draw two random matrices from the Yahiaoui of size n, and we form their generalized ratio. So G1 times G2 minus 1, okay. In one dimension, it would be just G1 divided by G2, but it's a higher dimension generalized ratio. And again, it's fairly straightforward to compute exactly the probability density on the set of n by n random matrices, which you can see on the third line. And in that case, the corresponding polar weight is a little bit more involved. Okay, it's some sort of factorial terms that don't matter a lot. 1 plus t power minus n plus 1. And it turns out that it's actually the multiplicative convolution of the Ginibre polar weight times its generalized inverse. Okay, so it's a nice illustration of what I mentioned before. And again, you can compute directly the joint probability density for eigenvalues, and you see it also has that nice structure where you get the squared van der Waals, or the modulus squared of a van der Waals determinant times product of its polar weight at certain points. So it's very, very nice to handle a kind of ensemble, right? So today, just to save some weight, I'm just to save some time, I'm gonna skip the technicalities and how we properly define this polar weight, but just know there's a full treatment, rigorous treatment, which is akin to the theory of polar frequency function, right? So I'll skip, so save some time, right? So now a brief word about the actual result, right? What's to come next. So remember that for today, I'm talking about two matrix model, right? This KP, right? And I'm going to draw K1 and K2, my two random matrices from such an aforementioned polar ensemble with polar weight omega. Think about the Ginibre ensemble when omega is exponential minus t, for example. And as I said, actually, to carry that computation exactly, it is possible to reduce the two matrix model to one matrix one simply by dividing by K1 on the left per se. I mean, factorizing is more accurate, K1 on the left. And as you can see, that two matrix model, AP K1 plus BP K2 is reduced to one matrix model where the one matrix is K1 minus 1 times K2. So it's a generalized ratio. But since we're drawing of random matrices from an ensemble that is closed by inverse and product, knowing the distribution of K1 and K2, we also know the distribution of K1 minus 1 times K2, which is also what we call a polar ensemble, with a polar weight being the multiplicative convolution that you can see in green here. Okay. And so we've also been able to derive an exact formula for the partition function in that setting, which is reminiscent of the first one I mentioned, and that was obtained by physicists in 2023 in the Gaussian case. Oops, sorry, it's a bit too fast here. Oh, that's annoying. Okay. Okay, so that calls for a few comments, obviously. The initial kernel has been replaced by Q twiddle and Q, which are m by n kernels reflecting the number of terms in the product building that partition function. Okay, and here they're actually non-trivial deformations. They're very hard to manipulate when m is bigger than equal than 2. As it turns out. So that's why for today I'm just going to talk about the case m equal 1, which is the average one. It corresponds to the average Wanning number. I should say it involves what's known as the Mellin transformation, which is some sort of multiplicative analog of the Fourier transform, in the multiplicative setting. And that's, it's not much more to be added there, I think. But it's an exact formula which holds for all values of m, just pretty hard to analyze as in the large n limit, right? Which is what we care for. So when n, so in the m equals 1 case, that formula actually boils down to what's in front of you. Okay, 5 minutes left. Okay, so that average Wanning number has a fairly simple asymptotic expansion, as you can see, where, so I'm just showing you a result in a simpler case for a specific choice of polar weight omega, albeit there's a more general treatment coming up next, which generalized the Gaussian weight, right? For example, when setting delta equal to 0 and gamma equal to 1, we recover the standard Gaussian case. And as we can see, the average Wanning number of the determinantal curves depends in a fairly non-trivial way on that parameter gamma, which indicates that there's effects that you cannot see when gamma is equal to 1. In particular, that subsequent term, right? I don't know if I can highlight it here, maybe there. Oh, no, I cannot. Right. Well, the gamma minus 1 divided by 2 terms vanishes whenever gamma is equal to 1, which implies that in the Gaussian setting, there are subsequent terms that one could not see before, right? So there's new subleading order terms that appears. In particular, the leading order of order n, the coefficient, which is an integral over the unit circle, right, depending on the parameter functions. In some cases, in some instances, this one vanishes. And so it was previously believed that the underlying physical system was in a topologically trivial phase, but it's not necessarily the case because the subsequent terms do not necessarily vanishes. There's beyond Gaussian effects, and the system is not necessarily in a topological trivial phase, which, as far as I can tell, is fairly new results. I'm moderately happy with that, let's say. And so obviously all of that calls for further investigation. In particular, just a brief word about that. It turns out that also at the level of the eigenvalues are not necessarily 2π periodic as well as the Bayes parameter ones around the unit circle. And some of them get permutated around when one winds once around, do one loop around the circle. And it turns out that the kind of permutation that can arise among those eigenvalues is highly constrained because this two-matrix model, in some sense, if you look at the discriminant of the characteristic polynomial of that two-matrix model, it induces a homogeneous function of degree nn minus 1, where n is the size of the random matrix, right? Which implies that this function, this discriminant, has n minus 1 zeros on the projective zeros, if you want, zeros on CP1, which are equivalent to nn minus 1 zeros on the 2-sphere, because the CP1 is topologically equivalent to S2. And when tracing a loop around the unit circle, it amounts to trace a loop around S2. And each of these zeros induce a branch cut on S2, identified with the Riemann sphere. And it turns out that every time crossing one branch cut, two eigenvalues get permutated because they change the sheet in the two covariant sheets on the neighborhood of those zeros, right? And so that geometric pictures allows us to explain the kind of patterns and permutation that arise in the eigenvalues of the random matrices as we wind along the unit circle. That's also the object of publication coming up next, I hope. It's certainly something for the next few weeks for sure. Okay, I think that's a good place to stop. I'm about to rush out of time, so I'm going to stop there. Thank you.
Okay, thank you, Matthew. And yeah, any question? Okay, if no questions, thanks, Matthew, again for your talk. Yeah. And okay, William, are you here?
Yep, I'm here. Can you hear me?
Yeah, I can hear you.
Oh, good.
Okay.
I need to share my screen, I guess.
Mm-hmm.
All right. Oh, I need to.
Matthew, could you?
Yes, I'm trying to stop sharing. My computer is not very responsive. I'm sorry. Can someone?
I try. Amazing.
Sorry.
Stop.
Laptop. I cannot stop sharing the.
Sorry
for that. I think I'm just going to hard reset my computer. Let's see what happens.
Oh. William, you could share a screen. Okay, yeah.
Okay, you can see this.
Oh yeah, now I can see that. Okay. And okay, good. And our last talk for today is by the William from the University of the Melbourne, and his topic of his talk is Fathian point process from the integrability in half space. Let's welcome William.
Yeah, thank you very much. Thanks to you for the opportunity to speak here. And I guess I should thank